So this is example number 3 for fastener under cyclic loading, cyclic tensile loading. Let's consider the same problem that we did, problem example 1, example 2. This is a completion of that example. And the load was shared up over 2 bolts. That doesn't change. And the preload was 1,200 pounds. We found that in the previous problem. Additional factors 1.2, 1.1 is required. So you know that your total design factor would be 1.2 times 1.1. And we show this gave you 1.32. Okay. Uh, and the problem is saying, just give me a sec. The problem is saying, uh, to determine if bolt is acceptable for fatigue, obviously, and you're basically going from a minimum of 0 to a maximum at 2,400. This is divided for both bolts, so one bolt will be half of that, and at 300 cycles per minute. Estimate the life if 99% reliability is needed. Now, this comes from tables, and this is given for this particular bolt, so this information is known. The second thing I want to do is I want to go to the table and find my fully uh, fully modified uh, endurance limit. And you can see that we are working at grade SAE grade 7, and my the bolt size was 1.5. So this is what I will be using. Okay, I could have used either one of these. I went with the smallest one. So I'm going to use this value. And these are the problems. In this case, since I'm using a value from the table, this is fully corrected, but does not include the temperature, and it does not include the temperature, neither does it include the reliability. So I need to include reliability because the problem says that it's important. Okay, so for my problem, my reliability comes from here. It says 99% reliability, and the value is 0.814. So temperature is 1. Nothing says about temperature, so I'm going to take temperature factor 1, multiply by this. It gives me this value. You multiply your S prime, that was 20.6 from the previous table, and you get this value. Okay, so this is 0.814 multiplied by this, and this is what we give you. This is the endurance limit I use for my problem. Okay, the second thing I want to check, I need to check for my fatigue resistance criteria. I need to make sure that this criteria is fully met. SP, AT. And I evaluated this. You can see this is 1,200. And this gave me, this is in pounds. And this gives me also in pounds. So you can see this is way smaller than this. So this condition is satisfied. That passes. So now I move on to find my maximum and minimum loads. And so your Pmax is equal to 1584. We found that in the previous problem. Your P minimum is going to start at a position when no P is applied. Then from here, you find what your F max is for the bolt, your F minimum for the bolt, and this is what you will use for analysis. This is C times P max plus your uh, uh, preloading, P minimum plus your preloading, and these values, you can see this is 0, okay? In this particular problem, this is 0 because I'm starting at the 0 condition, and that's very common because you have a bolt, you're not applying anything, you remove the load, you apply the load, you remove the load, apply the load. So that tends to be very conservative approach. So this is the loading condition that I'm going to really use in my problem. So if I want to plot this, you plot Respect to time will look something like this. It's always good to plot this. And this is 1648. This is 1200. Okay, this is your F. This is T. This is what you're using for your analysis. Okay, so the second thing next thing I want to find the alternating loads. So FA is equal to F max minus F minimum. You divide this by 2, and you will get this as 22381 pounds. And then your F mean will be F max plus F minimum divided by 2 will give you 1423 pounds. Okay, and then from here you calculate your stresses. Use your small a. That would be FA divided by tensile area that you get from the tables. You only got this. You don't have to use the equation I gave you because you only have this value. So that gave me 399.7 psi. Then your small s, that would be AT. You evaluate this. This gives you 4.4 psi. Now that you have your alternating and your mean stresses, axial stresses, we will go to the table to find your K. And as I told you, assume this is a cut thread unless something else is given. The grade size was 7, so this is where we at. So this is the value. So this is equal to 3.8. Okay. So now that we calculated this, the next step in my problem would be go ahead and do my checks. The first check is your static check at the maximum loads. To do that, you need to find your SA. That will be KFA times your small SA. This is 3.8 multiplied by 399.7. That gives you 5319 psi. Your M, your mean fatigue stress that we'll use in my problem. This is way conservative. If you use a correct approach, this might drop to maybe 1.17, but this is okay. This is what we will do in this example for this particular course. This is PSI, and then you calculate your S max. S max will be your alternating plus your mean, gives you 39.16 KSI. Okay, and you want to check your yield check. Factor safety and yield would be, remember, it's not yield strength, it's proof strength. But that's what we use for your fasteners. This gave me 1.105. This is from the beginning of the problem. You see this was given, or you find it from tables if you're gonna have the value 0.16. And that gives me a value of 2.68. This is bigger than 1, so static check is good. Now we move to fatigue. Fatigue assessment, there are 2 steps into this problem. First, let's go and find your sigma equivalent from Goodman theory. SA1 minus SM divided by SUT. And that gives me 7.13 KSI. Then I will do a yield check. That's the first check you do. SP divided by S equivalent. Make sure this is satisfied. 105, 7.13. This gives me 14.72. This is bigger than 1, not an issue. Let's go and see if the problem is infinite life or not. then your fatigue factor safety will be SE divided by S equivalent, and that gives you 16.85, 7.13. You get 2.36. It's bigger than 1. That means it's infinite life. Okay? So it's infinite life. I don't have to do anything else. And this basically is the conclusion of example number 3.